Guys, we're working on Lab 2 of Packet 3, and this is really a review of Lab 1. So we're still talking about polynomial functions and their graphs. Okay, so I just want to kind of review polynomial functions in kind of a different way. I really didn't cover this on the first video. If you're in class, I talked about it a little bit. So the first, like the smallest degree for a polynomial function is a first degree, and we're familiar with this with linear. And we remember y equals mx plus b, but we can also see it in upper level math, we see it as y equals ax plus b. So the x has a exponent of 1, so this is our first degree function because the highest exponent is 1, so we call this a first degree. All right, and then we move on to quadratics, which we've been working with this year. And now we say it's ax squared plus bx plus c. All right, so if you notice, the a represents the lead coefficient, and the highest exponent is the degree. And when we use a second degree, the next term should be the first degree, and we list them in descending order of exponents. All right, so if I wanted to write the general form for a cubic, it would look like this: ax cubed plus bx squared plus cx plus d. Okay, so the a always represents the lead coefficient or leading coefficient. Lead coefficient, leading coefficient, same thing. And the degree, in this case, they're using n. The n represents the degree. And the degree is the highest exponent. And it also equals the number of roots. And remember, the roots can be either real or imaginary. And only the real roots cross the x-axis, so they're called the x-intercepts. Okay, so basically that's a kind of a summary of what we talked about last class. All right, so now we're going to actually graph the pictures. So we talked about this a little bit in Lab 1. We're going to be more thorough with this in this lab. Okay, so the first one we're going to talk about is the quadratic. So again, the general form of a quadratic is y equals ax squared plus bx plus c. So this is a second degree, and it should have 2 roots. Okay, and since the degree is even, it's an even degree, this helps us to know about the end behavior, which is just what the tails or the ends of the graph look like. And since it's even, the tails are going to be in the same direction. And from this point forward, I'll probably just write tails same. But what I mean by tails same are they're in the same direction. Okay. And again, it's even because the degree is even. Okay. And 2 is the degree because the degree is the highest exponent. All right. So if you notice the first this first column, it says where the leading coefficient is positive. So they're talking about this a value, okay? And greater than 0 is another way of saying positive. Okay, this is just saying it's greater than 0, which is another way of saying it's positive. All right, so this whole column, we'll talk about positive lead coefficients. And the next column, it talks about when the lead coefficient is negative. So the lead coefficient is less than 0. All right, so if we have a quadratic and it has a positive ax squared plus bx plus c, okay, a positive a, then the lead coefficient always tells us about the right tail. All right, so this whole I'm going to actually extend this. If the lead coefficient is positive, basically all of these in this column, the right tail is going to be up. Okay, because the lead coefficient, if it's positive, that means the right tail is up. And this next column, since the lead coefficient is negative, the right tail must go down. Okay, so the lead coefficient and the right tail go hand in hand. All right, so I have an even degree. That means it's going to be a parabola, okay? And I need the right tail up, and the tails are in the same direction, so both tails are up. So this is my sketch of a positive ax squared. Okay, y equals, I guess I could put y equals positive ax squared dot, dot, dot. Okay. All right, and on the other side, the right tail is down. Both tails are in the same direction. So this would be a y equals negative ax squared dot, dot, dot. And if you notice, and again, this applies with this whole column. So there's only one turn, okay? There's one turn when it's a second degree. So the potential of number of turns is the just degree, the degree of the function minus 1. Okay, so parabolas or quadratics will always have one turn. One turn. And you can see that this is actually called a turning point. You may remember that from Algebra 1, where the graph changes either from going decreasing to increasing, or in this case, increasing to decreasing. All right, so we've moved on to cubics. So again, a cubic is a degree of 3, okay? So y equals ax cubed dot, 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 okay? This is the highest exponent. It's a third degree. Again, we'd expect 3 roots. The end behavior, well, since 3 is an odd number, our tails are going to be in opposite directions. Okay, and I mentioned odd, if you flip the d's around, okay, if we rotated them 180, it would look like opposite. So that's a way to remember that any odd degree will have opposite tails. All right, so it's a third degree. Actually, I'm going to do number of turns here first. So since it's 3 minus 1, this could have up to 2 turns. All right, so the first column, we said since the lead coefficient is positive, the right tail has to be up for this. And I'm going to turn once, and I'm going to turn again. So this is an example of a cubic with a positive lead coefficient. And I'm just going to put dot, 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 because we could have an x squared term, an x term, and a constant, or a combination of those. But the highest exponent is going to be 3. All right. With this example, I'm actually going to talk about the notation that we mentioned in the first lab. So basically this, I have a left tail going down. All right. So we say if a graph is, if we're talking about the left side, we're saying x is approaching negative infinity. Okay. Because on the x-axis, the negatives are on the left side. So this is basically saying the left side, the tail, or the y values, or sometimes they say f of x for the outputs, because f of x and y are interchangeable with function notation. All right, so on the left side, the tails are going down. All right, so this is basically saying on the left, the tail is going down. Okay, the left is negative infinity for the x, and the y for negative infinity would be going down. Or if we're talking about the right tail going up, we would say as x approaches positive infinity, that's on the right. Okay, we could have put a plus sign there, or just say as x approaches infinity, f of x is also approaching positive infinity because it's going up. So this is saying on the right side, okay, our graph is going up. So we need to kind of be familiar with this notation. Actually, I'm going to write that a little bit clearer down here because it's kind of squeezed in there. And we probably should put the positive infinity sign after I've thought about it for a minute. All right, that's a little bit better maybe. Oops. Just the right. Okay, so over on the next side, if we want a negative cubic, the right tail is down. We have the 2 terms, and this is what a negative ax cubed ... would look like. All right, so you should start seeing the pattern, which math is, there are lots of patterns in math. So a quartic is n to the 4th, so we're dealing with y equals ax to the 4th ... And since 4 is an even number, tails are the same. And they're either both up or both down, depending on the lead coefficient. So in this case, where the lead coefficient is positive, okay, I have a degree of 4, so it could have up to 3 turns. So 1, 2, 3. Okay, that's what a positive lead coefficient in a quartic could look like. Okay, so the number of turns, 4 minus 1 equals 3. 3 potential turns. Okay, this is where we have to start using the word potential, because sometimes if we get a quartic, and we saw this actually at the last problem, exercise 4 of lab 1, it was a positive lead coefficient, but we can also have the same with a negative. Sometimes it looks like this. In this case, since the lead coefficient is negative, the tails are going to be going down, but it kind of looks like a parabola, but it has a flat bottom. Okay, so it doesn't have to have 3 turns. That's not it has 3 potential turns. Okay, in this case, if you see a flat piece, it indicates that the degree is higher than the actual number of turns. Okay, so I just wanted to show you this possible graph so you know that a quartic doesn't have to have 3 turns. Okay, 3 potential turns. So this flat area indicates the degree is higher than turns plus 1. Okay, there's only 1 term. If we added a 1 to the number of turns, you would get 2, but this is not a quadratic. It's something higher because we have this flat piece. All right, and the last one we're going to talk about is a quintic. This is a 5th degree. So if I wanted to write a general start a general equation, it'd look like that. The end behavior, since 5 is an odd number, tails are going to be opposite. And to know which tail is up or down, we have to look at the lead coefficient. So for the first column, the lead coefficient is positive. So we have the right tail would be up, and we have 4 potential turns. So 1, 2, 3, 4. Okay, so this would be an example of y equals a positive ax to the 5th. There we go. Okay, so the quintic, if you want to try to draw the quintic with a negative lead coefficient, go ahead. Hopefully it'll be easy for you. Basically, it's going to be the reversal of the positive lead coefficient where the right tail is now down. So 1, 2, 3, 4, and this is a possible y equals negative ax to the 5th ... And again, so since our degree is 5, we subtract 1, and there's a potential for 4 turns. 4 potential turns. Okay, if we had less than 4 turns, one of those curves would have like a flat bottom. All right, so your homework is going to be to take the notes, obviously submit your notes, and you're going to complete this one on your own. Make sure you show work or write an explanation. Okay, you're going to finish number 2. I'm going to actually do part B with you right now, just so you have a heads up on what we're asking here. So it says answer each for the following. So these really correspond with the questions asked above. Okay, and it says put in standard form first. So really, the other two are in standard form. This is not in standard form. So the first thing we're going to do is rearrange this so the highest exponent is first. That negative has to go with the 8x squared because that's a negative term, and the 10 is positive. So this is what my function in standard form would look like. So now it says how many roots? Well, the roots is the same as the degree. So this would have 2 roots because it's a second degree. Okay. At most, how many turns? Well, if it's second degree, I'm going to do 2 minus 1, which it has 1 turn. Okay. It says tails opposite or the same. Well, since 2 is an even number, they're going to be the same. The tails are in the same direction. And the direction of the right tail. Well, since our A value, our lead coefficient for this one is a -8, the right tail is going to go down. So I'm just going to write right tail down. And I can just draw a down arrow, or you can write the word down. But so basically, this is what you're answering for 2A and 2C. Okay, so you're going to finish that one on your own. All right, number 3, I'm just going to talk to you a little bit about. This was a previous Regents question. And I just want to point out that it says consider the function p of x, which for p of x, they only give you the equation for. Okay, the graph below does not go with p of x. I want to cover up that x with a 5. All right, so this is p of x. And then this is a separate graph. This is y equals m of x. This is a separate function. So you should be able to look at m of x and have knowledge of m of x, but to see p of x, you would have to graph this on Desmos or the graphing calculator, or you can factor this and solve to find the roots as well to see if they're real or imaginary. Okay, and remember the real roots, since they're using the word real, you're looking for how many times it crosses the x-axis, or how many roots are actually real numbers. All right, number 4, you need to show work for. Okay, this is part of the homework as well, but you have to show work to get credit for this. And it's just review from, this is lab 7 of packet 2, solving fractional equations, if you want to look at your notes for reference. All right, so your homework is to submit your notes with those questions finished, and you can submit a picture, and you know where to find me for help. All right, have a good day.